Hi all, let's use our knowledge of the aldol condensation reaction and apply it to a molecule that can do an intramolecular aldol. Typically if you have a dicarbonyl, like we have in these two examples, most likely your professor is wanting you to make a ring, have the alpha carbon attack a carbonyl within the same molecule. The issue is, though, when you have a dicarbonyl, either a diketone, dialdehyde, or in this case an aldehyde ketone, there are several alpha carbons that could potentially lead to the enolate. Over here we have an alpha carbon, we'll call it alpha 1. Here's alpha 2, but see, that carbon doesn't have any hydrogens, so we can't make the enolate at this position. And here we have alpha 3. The idea is there an opportunity for the molecule to make either a 5 or 6-membered ring? I'll write that down here. You're aiming for a 5 or 6-membered ring. That's because you know that a 5-membered ring has a bond angle of 120 degrees. That's not right. 108 degrees for a pentagon. That's very close to a tetrahedral angle. And so there isn't a lot of angle strain when you make a 5-membered ring. When you make a 6-membered ring, if you put in the chair conformation, that angle should be very, very close to 109.5 degrees. So again, very little angle strain. What that means is that as this molecule is twisting and rotating and turning about in solution, it is more likely to have the right conformation to make a 5-membered ring or a 6-membered ring than potentially a 3-membered ring, right? That's very tight. What are the chances that while this is twisting, what are the chances that we'll have a bond angle at 60 degrees? Or even if you make a 7-member ring, that angle is a little bit too obtuse. Now we're not going to see it in these two examples, but there is a possibility that if the only ring you can make is a 7-membered ring, then chances are that's what your professor wants you to make, a 7-membered ring. But that's only by default. There are other examples that I know it's hard to visualize, but if you have something like a dicarbonyl that is already cyclic, for instance this, I am definitely getting way off track, but it's very symmetrical. So if we have this alpha carbon and you close the ring this way, you see that we're able to get 2 rings. One that is 1, 2, 3, 4, 5, and one that is 1, 2, 3, 4, 5, 6, 7. And that will happen, or that there's a good chance that will happen. I can't believe I went to this example before even showing you the more simple examples up here. So let's go back to this dicarbonyl example, because if I make the enolate at this carbon at A1, I can attack, oh, this looks actually good. I can attack this carbonyl right here, correct? And close the bracelet. And that bracelet will have 1, 2, 3, 4, 5 carbons in the ring. So that is correct. Because I can't make the enolate here, so this cannot be the attacker. But if I make the enolate here, and I attack the carbonyl across the way, do you see how that is not the ring that I am going to make? Because this would be a 1, 2, 3, 4, 5, 6, 7-membered ring. Now, here in the title I have predict the product, and then draw the mechanism. So let me show you what to do when you found which carbon is going to be part of the enolate and which carbon is going to be the one attacked. What's the best way to draw your final aldol condensation product? And we are doing the condensation. We are going to make a conjugated system. So let me redraw this and I'll show you what I would do. I'm definitely going to use this alpha, this one right here, and I'm going to make a connection between that alpha carbon and this dot. I know that, well, first of all, we're doing an aldol condensation reaction. Whenever you're under basic conditions and you're doing an aldol, you will definitely go to the condensation. You definitely do the dehydration. Now, whether that is conjugated or not depends on whether you have enough beta hydrogens, and we do in this case. You'll see what I mean in just a bit. If you know that you're making a 5-membered ring, don't worry about what's decorating that ring. Just draw the pentagon right away. We know we have a dot, and typically, I put the dot either here or here, so it's random. If I put the dot there, I know that the alpha carbon attacked the dot. So the alpha carbon can be either this one at 12 o'clock or this one at 4 o'clock, and I'll use this one. Now, you have to be very familiar with a typical aldol condensation product to be able to decorate your ring without drawing the mechanism. You should know that on this alpha carbon, see, nothing's happening to the left of it. So this carbon is not part of the ring. So that carbon is up here, and nothing's happening to that aldehyde. Okay. So right now, you could probably tell that we are making this bond right here. Now look at the dot. The dot has a methyl group. Okay. The dot has a methyl group, and in the initial attack, remember in the mechanism, you make an OH group here, OH group on this carbon here, but then you do a dehydration. Okay, that's a specific type of condensation. You condense water by kicking out the OH that was here, and the hydrogen, we do have another hydrogen here, that can be removed. So you're doing a dehydration, or you can think of it as an elimination. Now don't forget these two methyl groups. They're on the dot, but they're on the other side. So not here, but down here. If you feel more comfortable numbering, it doesn't matter how you number. We're not worried about nomenclature. We're just worried about getting the right number of carbons and the right connections. So maybe, where should I label? Maybe I'll label it from here. 1, 2, 3, 4, 5, 6, 7. That carbon number 1 is here. 1, 2, 3, 4, 5, 6, 7. And we have the two methyl groups and the two methyl groups. So that's how you get the ring structure. It's a 5-membered ring. Now, if you're asked for the mechanism, remember the aldol condensation is going to be 5 steps, starting with the formation of the enolate. Do you want to try that on your own? Go ahead and pause the video, and then when you come back, you'll see my mechanism for this intramolecular aldol, and it is an aldol condensation. So if you want to add condensation, that's fine. When I say just aldol reaction, what they're really implying is that you still have the OH group here. But because we're under basic conditions, you should go forward and make the double bond. Hopefully you can make the double bond conjugated if there's an opportunity that there's another hydrogen on this alpha. Do you see how there were 2 alpha hydrogens here? You strip off one to make the enolate, and you strip off the second one to get the dehydration. Okay, I know I'm talking too much. Pause the video, draw the mechanism, and come back and double check it for this reaction. Alright, did you all get 5 steps, right? 5 steps. Let me scooch up a little bit. Okay, so for this reaction, intramolecular condensation. Oh, by the way, we could verify, did we do an aldol condensation? Because typically you make what? An alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl. And your beta now is right here. From the carbonyl, you have the alpha and the beta. There's a double bond between the alpha and the beta. 5 steps. First form the enolate. Here's your enolate. Step number 1. Step number 2. Step number 3. You make what I consider the aldol product. See? Aldehyde, alcohol, aldol product. Not our final product, because now we have to do the dehydration. We're going to do step 4 and then step 5. Step 5 is the rate determining step where the leaving group leaves, and it does leave as OH minus. Okay, I know you've been drilled that OH is a bad leaving group, but when you're under basic conditions, and maybe if you add a little heat, it will take some time, but eventually you will kick out the OH minus, but also you make a very stable conjugated system. Conjugated means that you have a double bond, single bond, double bond alternating pattern. That is stabilizing. Okay, it's a stable product because you have all of these atoms are sp2 hybridized, and these pi electrons can actually be shared between these 4 atoms. So you're delocalizing the pi electrons because it is conjugated. I'll just write that down here. This is a conjugated, we call it system. I call it an enone, keto. In this case, it's an aldehyde. We'll go with enone. Okay. Alright, so that is all I want to say about this reaction. We were able to predict the product and draw the mechanism. Now, if we take a look at the second reaction here, for this dicarbonyl, we have several options for the alpha carbon to participate in making an enolate, but also that molecule is symmetrical, and that simplifies our decision making quite a bit, because whatever we do on the left, we can do the same thing on the right and get the same product. So I'm just going to focus on either this alpha carbon 1 or alpha carbon 2, and whichever one you make the enolate, you're going to attack this carbonyl. Do you guys want to give this a go? Decide which alpha carbon you want to deprotonate to give you either a 5 or 6 membered ring when this side of the molecule, either one of these 2 carbons, attacks this dot. Draw your ring. Make sure your product is going to be an alpha beta unsaturated, looks like it's going to be a ketone, and then draw the mechanism. So when you pause the video, do that, and when you come back, you'll see my final product and also the full mechanism. Okay, welcome back. The final product that I have for this reaction is this ring here, and the mechanism, I think I could get it all on the screen right there. Okay, go ahead and double check your work. If you made a mistake, don't erase it, don't white it out. Go ahead and cross out your mistake and then draw the correct molecule or add whatever you need to add. You know, when I'm grading, I'm looking for charges. I'm looking that every arrow starts either from a lone pair or a bond, and I'm double checking the connections and the number of carbons at each step.